So I'm going to present some work, which is joint work with Carl Rasmussen and Dieter Fox on Gaussian processes for data-efficient learning in robotics and control. If we look at robotics and control problems, we essentially face three key problems. One is modeling, one is predicting, and one is decision-making. For example, if we look at this, this robot arm over here, we might be interested in modeling the robot's behavior for a given control strategy and use this model for predicting the outcome, or say trajectories, for example, of this end effector, this table tennis racket, in order to predict whether we are actually able to hit this table tennis ball. And if we don't do that, we might want to change our control strategy. That means we end up with a decision-making problem. What is the best thing to do in order to hit this table tennis ball? And machine learning in robotics and control is getting more and more interesting because our engineering, let's say, capabilities end at some point when we have to model very complicated relationships, for example, effects of springs or compliance in these robots. It's very difficult to model. So by using some, say, adaptive machine learning methods, we can reduce the engineering effort, and we can also increase the level of autonomy in current robots and control systems. However, there are also some challenges. And one is we need to deal with uncertainties and unknowns. And we also need to do something about data efficiency. For example, if we look at, say, decision-making problems in general, then you can think, oh, this is a reinforcement learning problem. But if you look at how many, say, trials a reinforcement learning algorithm like Q-learning or something like this needs to, in order to achieve something useful, that's completely unfeasible with robots because you can't run millions and millions of experiments with a robot because it's A, time-consuming, and B, at some point you're also going to break the robot. So in this talk, I'm going to address this problem, and I'm proposing a practical framework, reinforcement learning framework, for learning from scratch in robotics and control. So if we look at reinforcement learning, so the reinforcement learning setup in this talk is that we have something that's called the state that kind of like summarizes the, say, the configuration of the robot, for example, and we say the state at time step t plus 1 is a function of the state at time step t and the controlled signal at time step t, plus some noise which we assume is Gaussian. And the control itself is a function of the state and some policy parameters, and this function is called the policy. One of the crucial things is that this function f, this transition function, is unknown. So if we talk about full autonomous learning, we can't plug in, or we don't want to plug in any, say, specific prior knowledge about the dynamics of the robot. And then the reinforcement learning problem is basically saying, oh, we want to find policy parameters that minimize some expected long-term cost. And this expected long-term cost, j of theta, so it depends on these policy parameters, is a finite horizon sum of expected costs at each time step. And this cost function at each time step could, for example, be a squared penalty between, let's say, where you are now and where you want to go to at the end. We also assume that the initial state is Gaussian distributed. So this kind of objective is a typical objective in optimal control and reinforcement learning. At a very high level, the difference between optimal control and reinforcement learning is that in optimal control, we assume that we know f, and in reinforcement learning, we don't. So let's have a look at this reinforcement learning problem. So I'm going to introduce a conceptually very simple idea of how to solve this reinforcement learning problem. In the first step, we learn a probabilistic model for this transition function f that we don't know, that corresponds to some sort of system identification step. Then we use this model for predicting long-term predictions of the state evolution for a given controller parameterization. Then we improve the policy in order to minimize this cost function. And then we apply the controller to the system. So conceptually, I think relatively simple. And let me go through all of these steps a little bit in a bit more detail now. So let's start with this system identification step. So the system identification or model learning is effectively a regression problem. So we are looking at finding a function x, that maps x to y values. In this illustration, let's assume these y values are noise-free, so we actually know exactly what the function values are, the corresponding inputs. So that means the model learning problem is solved if you find a function that connects all of these data points. So here's a function. So now I said earlier, we're not done with modeling, but we also want to do predictions and decision making. So if we now take this model and ask, so what happens at x equals 7, then the corresponding function value tells me, well, it's around -1, and I take this prediction, and now I make a decision. So now imagine that I'm, say, walking along a cliff, and this -1 tells me I need to do a step to the left, and say positive values would say take a step to the right. I'm not sure, would you make that particular step given the data and this prediction? I'd say we might disagree whether you would or would not, because you could also find other plausible models that give you different answers. So, and whatever model you choose, you will end up with some sort of model errors because none of these models is actually correct and probably not even close to correct. In order to be a bit more robust to these kind of model errors, what you could do is you could put a probability distribution over plausible functions and then ask this probability distribution, so what's going on at x equals 7? So then this model says, well, I think on average it's 0, but I have no clue. And if you take this no clue into account when you make decisions, you're much more robust to these model errors than picking any deterministic function for this transition function. So therefore, we really need to express the uncertainty about the underlying function to be robust to these model errors, and we implement this, say, probability distribution over functions by a Gaussian process. So fortunately, we already had the introduction to Gaussian processes, so it's always good to be the last one in the Gaussian process section, so I don't even have slides for that. So we use this Gaussian process now for this transition function, and now let's have a look at how we use this Gaussian process model for long-term predictions for a given controller parameterization. So let's say, in an illustration, we are interested in predicting our initial state distribution over time, iteratively through this Gaussian process model until we reach the final time horizon. If we now take one of these time slices out, the problem boils down to, say, mapping a Gaussian distribution, which we have on states and controls, mapping this one through a Gaussian process. And if we do this, we end up with this shaded probability distribution over here. And in order to get this probability distribution, we need to solve this integral, triple integral, where we integrate out everything that is uncertain. So we have a probability distribution over states and controls, and we have a probability distribution over functions. And if we do that, say if we integrate out all of these uncertainties, we get this shaded distribution. So unfortunately, we can't compute these integrals, but we can compute an approximation. So we can compute the mean and the variance of this shaded distribution in closed form. That means we can do a Gaussian approximation to this shaded probability distribution, take this Gaussian then at the next time step, and then feed it again through the Gaussian process, do another Gaussian approximation here, and then cycle through, and then obtain this sequence of probability distributions over states for a given controller parameterization. And all of them are Gaussian approximated. So now let's have a look at how we improve the policy by using these kind of predictive probability distributions. And this policy improvement step consists of two steps. First, we compute the expected long-term cost, and then we minimize this long-term cost. So we already know how to predict these kind of state trajectory for a given controller parameterization. And now, in order to compute this j of theta value, we simply have to compute these expected values at each time step, which boils down to integrating a cost function against a Gaussian distribution. If we choose this cost function carefully, say polynomials, so some sort of trigonometric functions, Gaussian-shaped functions, then we can compute this expected value in closed form. And the nice thing is, up to this point, we have done everything analytically, so I can write down a more or less lengthy equation that can give you an expression for this particular cost function. And that also means we can analytically compute the gradient of this cost function with respect to the parameters, and then use a standard gradient-based optimizer for finding parameters that minimize this cost function. So I have done that for you, so if you want to play around with the code, it's available. I strongly advise everybody not to try to code up these derivatives without having a look at this code. So, and now we're ready to apply the controller. So let's demonstrate more like how this learning framework works. So the first thing we did was we applied this controller learning framework to a standard benchmark problem. This is called the cart pole swing up. So the idea is that we have a cart running on a track with a freely swinging pendulum attached to it. So the state was the position and velocity of the cart and the angle and angular velocity of the pendulum. And the idea was that initially the pendulum was hanging down. We wanted to find a nonlinear controlled strategy that swings the pendulum up and balances it in the inverted position like indicated in this picture. So we didn't use any knowledge about the nonlinear dynamics because we wanted to learn from scratch. And as a cost function, we penalized the Euclidean distance between the tip of the pendulum and the target position, so this crossover here. And this is how it works. So initially, we collect a small set of a small data set by applying random actions to the system in order to kick off the Gaussian process model learning part. So when we have the model, we go back. We learn this controller, and you can see that iteratively it automatically figures out how to solve this problem. And after, in this case, after 7 trials, it solves the problem, and in a test run, it also is. We can see that it's relatively stable. Note that we only penalize distances, no velocity, so it's pretty good, and it's even robust to small disturbances because the controller we learn in the end is state feedback controller. So that was very encouraging. And the nice thing with benchmark problems is that other people do them as well. So if we look at some literature, so I have references to other papers where they solve the same problem, so swing up pendulum and balance it in the inverted position. In the, on the y-axis, I have the required experimentation time in seconds. This is on a logarithmic scale. So here we are talking about days of, well, in this case, I think in actually all cases, simulation. So days, hours, and minutes. Compared to these methods, we are here. So we are an order of magnitude faster than these methods. And we can report an unprecedented learning speed compared to state-of-the-art reinforcement learning methods. So the next thing we did, we were applying this idea to automatically, let's say, controlling a robotic manipulator for stacking a tower of blocks. So we use a 3D, or we use a predecessor of a Kinect camera for tracking the block in the gripper of the robot. The robot was very fragile and noisy, so you can't run many experiments without reassembling the robot and replacing parts. And the same idea was applied, so we learned the forward model, so this transition model, and the controller from scratch. And the outcome is illustrated in this video. So here is just an illustration how, let's say, noisy this robot is. So by just tapping at the bottom, you have like a radius of, in the end effector of swinging is about 2.5 centimeters. And so the Kinect camera here is looking at the scene. It's just tracking the block in the gripper. We don't have any information about the joint state of the robot. So the model we learn effectively is a 3D block flying through space when we apply control signals. you can run approximately 50 experiments with the robot before the gripper falls off, and about 250 experiments before you have to replace some motors. So fast learning is really crucial here. It's a good motivation. Yeah. And so this kind of like learning, this block stacking learning was relatively robust. So I demonstrated this for like a full day at the Intel Open House in Seattle, and it was pretty robust. All right, so the algorithm has been applied relatively widely to quite a range of robots. For example, here we have more like it's called a Robotino platform. It's an omnidirectional platform with an elephant trunk manipulator, so we use this for learning to grasp. Here's a compliant, biomechanically inspired robot that was used for hitting table tennis balls. This one is a lightweight KUKA robot arm for basically curling. Bosch used the method, so I was not involved in these projects. So Bosch used it for controlling throttle valves in combustion engines, and that seems to work relatively nicely. And Andrew McHutcheon in Cambridge used it for pitch controlling a unicycle, or learning a pitch controller for a unicycle with exactly the same ideas. So now you might ask, well, do we actually need all these probabilistic models? Why don't I just use a deterministic model? And I think, let's say, it's an interesting question because you would save a lot of computation time if you could get away with a deterministic model. So we evaluated that a little bit. So we compared two models. So we use a Gaussian process as the probabilistic model for this transition function. And then we used a deterministic model where we just took the Gaussian process and threw away the variances. So you could call this a deterministic Gaussian process, but it's still a non-parametric model. Let me just demonstrate what the outcome is. So this is again the card pole system in an, let's say, illustration. So here we have the cart running on a track, and what I've shown now was the initial trial that we use for kicking off the learning. This ellipse shows at the moment the initial state distribution for the position of the tip of the pendulum, and say if I now restart this, you will see that this ellipse is growing, and this is indicating, is representing these long-term predictions which we do for the evaluation of the cost function. So there's no, let's say, measurement updates for included here for updating these ellipses. And here there will be a bar coming up at some point showing you the immediate reward, so there's a negative loss, and if the bar is to the full right, then we have full reward. So this happens now with the normal Gaussian process model. So you can see that initially the uncertainty explodes, but the model gets better and better while it's like collecting the data, and after 3, 4, 5 experiments, it basically solves the problem. And even these long-term predictions predict that it's really certain with almost full probability in the target. So now let's do the same experiment with the deterministic model. So we use the same initial trial for kicking off learning. And this is now what happens. So the deterministic models has really bad extrapolation properties. I mean, the full model, the full probabilistic model too, but it has uncertainty associated with it. And these uncertainties, these model uncertainties, are really crucial for getting anything out of this model. So if you have a deterministic model, you have to make sure that you add additional exploration terms in order to get this working. And if you don't do this, this is what happens. It learns to basically stay where it is in the beginning because that is the closest to the target it can predict. because if it moves away from this position, the tip of the pendulum, if it always hangs down, it's like the distance is getting bigger and bigger. So it learns something sensible, but it doesn't learn what we actually want it to learn. All right, so we ran a couple of experiments with different initializations and so on. So we get about 95% success rate with the Gaussian process and 0% very consistently with the deterministic Gaussian process. So then let me conclude. So I presented a practical framework for data efficient learning or reinforcement learning. We achieve an unprecedented learning speed, and the key to success of this method is the explicit incorporation of model uncertainty into modeling, predicting, and decision making, and we applied it to a bunch of real systems. Thank you very much for your attention.
Questions?
Thanks, that was really interesting. I had a question about the policy piece. It seems especially for these complicated robots like stacking blocks, how you represent the policy in a parameterized way must be interesting and important, and I'm wondering, is there a standard way to do that, or is your choice of policy representation also a really important differentiator between approaches?
Right, so there are some, let's say, technical issues which we need to ensure, so you need to be able to map Gaussians approximately through these policies. So what we use in practice is a radial basis function network as the policy, where the free parameters are the locations of the basis function, the weights of the basis functions, and the shared width of the basis functions. So it's a relatively flexible model for policies. There are a couple of things you need to fix, like the number of basis functions, for example.